Hello, Miss Aguilar again. All right, we're going to go over the graphing practice problems. This is from the packet I handed out on Friday. Let me just go through these as an example, and hopefully you guys can follow along and see maybe where you may have made little mistakes, or maybe you can follow along with this and you've done everything perfect, which would be fantastic and is highly likely. All right, so first, I always recommend reading the directions with anything I may give you guys. I give you everything you need. You just have to do a little bit of reading. Okay, so for each data set below, determine the mathematical expression. This handout says expression, mathematical expression. It just means mathematical model. So you'll hear these two terms interchangeably. You'll hear mathematical expression and mathematical model. They're the same thing. All right, to do this, first graph the original data. Assume the first column in each set of values to be the independent variable and the second column the dependent variable. So looking here at this data table, our first column has mass, and this is our independent variable. So we graph this on the x-axis of our graph. And then looking here, in the second column, we have force, and this is the dependent variable, and we graph this side on our y-axis of our data table. Of our graph. Taking clues from the shape of the first graph, modify the data so that the modified data will plot as a straight line. This is just telling us to do a best fit line using the data points we put in our graph. Using the slope and y-intercept of the straight line graph, write an appropriate mathematical expression for the relationship between the variables. Be sure to include units. This is just telling us that we're going to move forward and we're going to make a mathematical model. All right, so let's just use this data here and plot it in our graph. But before I do that, let's just kind of go over this real quick. So I've set up this data table here ahead of time, the graph, just to make it a little bit easier. So we have our force versus mass title, and then you can see the formatting of this is correct. We're a dependent variable versus the independent variable. Our force is the dependent variable, so it's on our y-axis. The N is for newtons. The abbreviation for newtons is actually capital N. If you write in newtons, that's fine because you don't know that the abbreviation for newtons is N. And it's in the parentheses because when we do our units for both axes, the units go in parentheses on the side where we're labeling them. And then we have mass as our independent variable with units of kilograms, kg, in the parentheses. All right, so let's just start off here. We're going to have 0, 0 as our first data point, and then 1.0 and 5.6. So, whoops. Sorry guys, let me just fix this real quick. Okay, so let's just plot our data. Let me kind of make this a little bit bigger. It's a little bit easier for me to see. Okay, so our first data point is 0, 0. So I'm going to put a data point right there. The next one was 1 and 5.6. If you see here on the y-axis, I have labeled these so every other line is labeled and it's in increments of 5s. But these lines in between, like this line here, are 2.5. Say 2.5, 5, 7.5, 10, 12.5, 15, 17.5, 20, and then 22.5, which we won't use, but it can extend up to 22.5. So our first data point is 1, 5.6. So we look at the 1 as our x, and then we go up just slightly above that line, and that's 5.6. Remember, it doesn't have to be exact because we're making a best fit line. But you want it to be very close to the correct points. So then we have 2.0 and 7.9. So then let's look here. We have 2 and then 7.9. Now remember, this line here is 7.5. So 2 and then 7.9. So I'm just going to put it right about there. Okay. All right. And then our next data point is 3 and 12.6. So we have 3 in our x, 12.6 on our y. When you're doing this on your own, make sure you go a little slow. Whoopsie, I shouldn't have put it there. Like I said, make sure you're looking at all the data points. So this is 10 and the next one was 12.6. Let me double check. Yep, 12.6 would put us right here on this second line, on this line right here. So it's 12.5 and 12.6 is just above that line. In fact, maybe even partially on that line. And then we have 4 and 15.9. So 4 on our X and then 15.9. So again, just barely on the line. And then we have 5 and 20.5. So here we go on 5 and then 20.5. Just trying to follow these lines up. Right there on that line. Okay, so all of our data is plotted out, and then you're going to make your best fit line. So let's use a different color just so we can see our best fit line. When you guys are doing this, make sure you do your very best to get it through at least 1 or 2 data points, because it will just be much more accurate. But of course, don't manipulate your line so it looks sort of like a dot to dot or a line, you know, dot to dot. You want it, basically the term of what it is a best fit line. So, and since we have one of the data points on 0, 0, that's actually going to end up being our y-intercept. So you guys, I'm just really freehanding this here. Okay, there you go. There's our best fit line. All right, now with our best fit line, the next step was to make a mathematical expression, right? So it's saying here a mathematical expression or a mathematical model. I have set up a little spot over here to look at making our slope. So first thing you need to do is calculate your slope and then calculate your y-intercept, or to visualize where your y-intercept is. So here I've done that. I have set up the equation for our slope. We have y2 minus y1 over x2 minus x1. So let's pick 2 points on our graph. I'm going to go with this point here. Oh, darn it. Sorry. I accidentally erased it. All right, there's our best fit line. I actually erased a data point, which was right about there. So let me pick 2 points. I'm going to pick this point here. Let me just change it. And I'm going to pick, why don't we pick one that's actually right on the line, and we can use that. That's an actual data point. All right, so this is my x1, y1. And this is my x2, y2. So what are those values? We have here 0.5. We have 0.5 kilograms. And we have here, it's 2.5. 2.5 newtons. And then this is actually a data point right here, and that is 4. And I think it's 15.6, right? Yep, or 15.9 and 15.9. So we'll use these two data points. So let's put that into our equation here. So y2 is 15.9 newtons minus y1, which is 2.5 newtons. Make sure you include those units now that we have units. And then our x2 is 4 and our x1 is 0.5 kilograms. So then you just go ahead and you do the math, right? So you have 15.9 minus 2.5. So that top number there is 13.4, and then you have 4 minus 0.5. 4 minus 0.5 is 3.5. So you have 13.4 over 3.5. And remember, this is not complete. This is a division problem, and we have to then go ahead and divide 13.9 and 3.5, and I end up with 3.82857143. And remember, we're doing two decimal places, two places to the right of the decimal or to the hundredths place, and that will give me a value of 3.83, and that is our slope. 3.83, and I've included the units there, newtons over kilograms. So this is our slope, or we can call it m, because remember, our format for our equation or our mathematical model follows the y equals mx plus b format. This is our equation of the line. This is our linear equation, our slope y-intercept form. But we're going to use this template and make our mathematical model out of it. So let me just write that up right here. So for y, if you remember, y on our our variable here, y is force. So let me fill that in. So our y is force. This is the first part of our mathematical model, and that's equal to m, and we were able to calculate our slope, or our m value, right here, 3.83, and be sure to include those units because we have a number there, and anytime you have a number, no naked number, sorry, that k is kind of funky, and then we have our x, right, and our x value, or x variable, I'm sorry, is mass, so go ahead and write in mass. And then plus b. Plus b is the y-intercept. So let's take a look. Our line goes right through the 0 there, and so our y-intercept is 0. If this was an actual numeric value, like anything above 0 or even below 0, it can be a negative. Just make sure you include the units for the y variable, and those units are newtons. So since this is a 0, you can actually leave it off or include it, but you won't have to put any units if it's a 0. So there you go. This right here is the mathematical model. That's the mathematical expression. I'm just going to put math period as a kind of abbreviation. All right. Well, I'm running out of time, you guys, so I think I'm going to stop here, but move on to that next video, and I'll show you guys how to figure out how the variables are related, what does the slope represent, and what the y-intercept represents for this graph. So just move on to the next video, the second part of this graphing practice handout. All right.